Okay, part 2 of the word problems, growth and decay. These I think are a little bit easier than your money problems because the formula isn't quite as brutal. First, let's do a growth problem. This is used mostly for population dynamics, bacteria growing, stuff like that, rabbits reproducing on an island, you know how they get. This is a growth problem. It's not very realistic because this growth problem assumes that there's an unlimited amount of space, unlimited amount of food, no predators. It's called exponential growth. And basically it just says that they'll just grow and grow and grow and grow and grow and grow. And this is the formula we use. Notice it should look familiar. This should look a lot familiar because it's the same formula we used for continuous compounded interest with our money problems. So it should be pretty similar. It's just we're dealing with living organisms instead of money. But you have the final accumulated amount. P is the initial population, which in money was the initial deposit. R is the growth rate, which in money was the interest rate. And pay attention to the units, because sometimes the growth rate is given per day or per week, and that affects your time. And so then you have T, which is time. So let's do, oh wait, then I need to have the decay, yeah. So there's our formula for growth, which is just your PERT formula. A decay problem, I use a formula that's a little bit different than you'll see in your book. This just works so much more sexy-like than the other books, than the other formulas. Radioactive decay is used for carbon dating. That's the main thing. There are other things. I got kind of generic here, other such things. Kind of a cop-out. But anyway, here's our formula for radioactive decay. And this relies on you knowing the half-life. So I will give you problems that we're going to do half-life problems. A is still the final amount. P is still your initial amount. T is still time. Only difference here is we have half-life, which is usually given in some kind of a time. It could be weeks, could be days. And the unit for half-life will affect the unit you use for time. So I have 3 examples. The first one is a population of gnomes that is growing. So as soon as I see population growth, I know we are dealing with PERT, so P-E to the RT. And I'm going to pull out my given information, a rate of 4%. So I know my rate is 0.04. And notice it's every week. So my unit of time is going to be in weeks. I have 14 gnomes in my attic, so that is an initial amount of gnomes. And believe me, you don't want gnomes in your attic. It's hard to get rid of them. And how many will I have after 6 weeks? So T is going to be 6, which means we don't know what A is. We're looking for how many we have. So let's throw all this in. A is going to be 14 times E to the 0.04 times 6. And we will simply throw this in a calculator. And I'm going to pause it while I do that. And I get A to be 17.797. I'm not going to do the screenshots of the calculator this time, but that's what you get when you punch it in. Just make sure you watch your parentheses. Make sure you get your exponent in parentheses. Now, remember, we're dealing with living things here. We are probably not going to have a part of a gnome in my attic. You're either going to have one or you're not going to have one. So what's happening here is our gnomes are in the process of producing that 18th gnome. We don't have one yet, so we will always round down on these problems when we are dealing with living organisms. So we will need to start with 17 gnomes. I'm sorry, we will have 17 gnomes at the end of 6 weeks. So there we go. Now let's try another one. Okay, some cats want to destroy the gnomes in my attic. They need 100 cats to win the battle, but only have 72 right now. Population grows at 9% every day. After how many days will there be enough gnomes? So this is another growth problem. So A is equal to PE to the RT. Let's see, they need 100 cats. That's a desired amount. That's going to be what we want to accumulate. So we want 100. We have 72 right now. The initial population grows at 9%, so R is going to be 0.09, and that's per day. And I want to know after how many days, so I want to know what T is. We don't know what T is, so we're going to throw in everything else. So A is 100, P is 72, E to the 0.09 T, and we're going to solve this for T. We're going to start by dividing by 72. Divide by 72. So I have 100 over 72, which probably reduces, but I don't care, because we're going to throw this all in the calculator at the end anyway. equals e to the 0.09t. Now my variable is in the exponent, so I will need to take the natural log of both sides. I'm going to take the ln of that times the ln of this. And ln of e to something is just the something. That's one of the properties of logs. So we have 0.09t is equal to ln of 100 over 72. And then to finish solving, we will divide both sides by 0.09. Over here, they're going to cancel. Over here, we divide by 0.09. We'll throw that in the calculator. Make sure you watch your parentheses. Okay, so I throw that in the calculator. And according to this model, the cats will have enough to take over the gnomes in 3.650. My unit is time, or my unit is time. My unit is days. And you can have part of a day. You don't have to have a whole day or no day. There is a part of a day, so I'm okay with the decimal on this problem. And there's our answer, 3.650 days. The gnomes will take over, or the cats will take over the gnomes. Thank goodness. Okay, last problem. A gnome poops in my kitchen floor. The poop radioactively decays and has a half-life of 8 days. Okay, this is a half-life problem. The half-life formula was A equals P times 1/2, or 0.5, to the T divided by the half-life. So as I'm reading this problem, it says the half-life is 8 days. So H is going to be 8, and I'm going to make note of my time. It's 8 days is my half-life. If the initial stool sample weighed 23 pounds, now that's the initial amount was 23 pounds. How much is left? So we want to know how much is accumulated after 7 weeks. Now here I'm trying to be tricky because I gave you 7 weeks. And what's tricky about that other than my jacked up W's? Shut up. 7 weeks. Ooh, my half-life is in days. So what we have to do is actually convert 7 weeks to days. And 7 weeks is going to be 49 days. So make sure you make sure that That's redundant. So to be sure that your units line up, especially for the time and half-life and rates and stuff like that. So A, we don't know. My initial amount is 23 pounds. Half-life, 0.5 times 49 over the half-life, which is 8. And we simply throw that in the calculator. Make sure you trap your exponent in parentheses. You will get the wrong answer if you don't do that. So let me throw this in the calculator. And I get an answer of 0.3295 pounds. And I'm a fan of rounding to the third decimal, so when you round that to the third decimal, the 5 is going to round the 9 up, which will actually pull that 2 up, so it's going to be 0.330 pounds. And the reason I like 3 decimals is because that's the standard on the AP Calculus exam, and I just kind of stick with it for pre-cal. So those are some growth and decay problems. A short video, you should be thankful. We never have an 8-minute video, so yay me.